on the shape of context. Take it away.
Thank you, Ulrich. Yeah, so so this is my second talk in these 4 days, and I didn't realize that I'm almost the only person who I think submitted like 2 talks to this workshop. So thanks for giving me the opportunity. This one is going to be a bit shorter, and so, but it's very nice to talk after Josh, because it's I'm talking about very similar ideas. I'm not going to be talking about inverse diagrams, but about direct categories, but that's purely convention. But I'm going to have a slightly different take on it. So they are not used to represent dependency structures, but contexts. So I think it's it's definitely related, but it's slightly different. Okay, so let's get started. Okay, so initially this talk was inspired by a talk by Martin Leuven in 2014 at the Institut Henri Poincaré on this workshop on constructive mathematics and models of type theory. And he had some vague ideas about these shapes of contexts and what context should be in type theory. I think if anybody remembers that, please, we can talk about it later. I would be interested to hear other people's recollections. And then these ideas were developed in discussions with Mathieu Anel, who we've heard, Carlo Angioli, Chaitanya, who we've heard several times from the sky, I think, because he asked questions over Zoom, and Andrew Swan, who is also here. Okay, so motivation. Simple versus dependent type theory. In simple type theory, like simply type lambda calculus or propositional, let's say intuitionistic logic, we can think about contexts as flat lists. And I mean, typically what we write is we have a list of variable declarations that should be a subscript, and then we have a conclusion or a term of a certain type, and we can permute these variables because there are no dependencies between them. So in dependent type theory, well, we do have dependencies. So the second variable, the type of the second variable in the context may depend on the first variable, and so on up to the nth variable may depend on all the other variables that come before. And so the picture I want to visualize as a kind of a linear order that I draw vertically. And that's also reflected in, for example, in contextual categories. Contextual categories have this grading on the objects by integers, by natural numbers, and so there we have an explicit length of a context, and that reflects this structure. And then we have a parent function that sends the context to its, like, removing the last declaration. But if we think about like specific examples of dependent contexts, then we don't always have this linear form. And so, for example, here's the generalized algebraic theory of categories. So I already had this on my slides on Tuesday. So this is how you define categories as a dependent structure where you have a sort of objects and then a sort of arrows that depends on 2 variables of the sort of objects. So for every 2 objects, we have a collection of arrows, and then identity composition and axioms. And for example, if we look at the shape of this context here, of the declaration of arrows, well, there's no dependency between the variables, so actually it's flat. If we look at the shape of the context of composition here, we have 3 object variables, 2 arrow variables, where the first arrow goes from x to y, the second goes from y to z. So these variables depend. So So the f depends on the first two variables, the g on the second two, and we get this picture. It's like an M. So that's what I want to call the shape of this context. So maybe if we want a more realistic representation of the shape of dependent contexts, maybe a more fine-grained analysis would be given by taking posets instead of arbitrary finite posets instead of linear orders. Well, it turns out that posets are not enough. And what we really want is direct categories. And I want to motivate this by looking at this diagram in the syntactic category of the theory of categories. So recall that the syntactic category has contexts as objects and substitutions as variables, as morphisms. And so in this case, so we have a context of length 1 here, context of length 2, this is the diagonal, and here we have projections from longer contexts to shorter contexts. So with the context with one arrow depending on two variables, and this is projected down. And if we pull that back in the syntactic category, then we get the context with one object variable and one arrow variable that depends, that's an endo arrow because it depends on, in the source and target, on the same object variable. And so these arrows in this diagram, they are all, so these are projections, that's what I call display maps on Tuesday for the people who were here. But these arrows are also of a special case, the horizontal, because they only contain variables, so they are variable renamings. And this kind of arrows I want to view contravariantly, this should be contravariantly, over the shapes. So for example, this projection corresponds contravariantly to the inclusion of this flat shape into this shape of this context. And well, and the diagonal corresponds contravariantly to the terminal projection from this to this. And then I want this pullback here to correspond to a push out. Well, and if we formed the push out in posets, this would be just an interval, but it turns out this is not well behaved. So to get something well behaved, we have to form the push out maybe in categories, and then we get something like we have two lines here, that's two parallel morphisms. And that reflects the fact that the variable f here depends twice on this variable x. And okay, so in which category does this push out live? It lives in the category of finite direct categories and discrete fibrations. So these are definitions where we have seen the duals already 20 minutes ago. So a category is direct if it has no finite inverse paths, or there are no infinite descending chains of arrows, of non-identity arrows. And a category is called one-way if the only endomorphisms are identities. And so one can show that direct categories are one-way and skeletal, and for finite categories, that's an equivalence. So a finite category is direct if and only if it is skeletal and one-way. So no endomorphisms and no isomorphisms. And so, yeah, so then I want to call FDC the category of finite direct categories and discrete fibrations. And somehow it's an empirical observation that so this variable renamings should be the contravariantly over discrete fibrations. So I don't really have a good explanation for that, sorry. So, okay, And it turns out that among the discrete fibrations, there's a special subclass, the injective ones, and they are sieve inclusions. So in a poset, a sieve is simply a downset. And in finite direct categories, it's a bit more general, but you still have something like downsets. And so these sieve inclusions, they correspond contravariantly precisely to the projections. So if I have a context of a certain shape, then I can always omit terminal nodes to go to a shorter context, and that's then this inclusion of the diagram with the omitted nodes, with all the nodes included, is a sieve inclusion. And yeah, so it turns out that these sieve inclusions are close under composition, and sorry, this should be push out here in FDC, and initial inclusions are obviously injectives, and that means that FDC is a co-clan with sieve inclusions as co-display maps. So I didn't include the definition of co-clan. It's dual to the definition of a clan that we've seen on Tuesday, but it means precisely it's a category with an initial object and a class of arrows that is closed under composition, contains isomorphisms, and it's closed under push-out along arbitrary maps. Yeah, that's it. And so clans arise as syntactic categories of generalized algebraic theories, and we can express what a model of a generalized algebraic theory is by as functors out of the corresponding clan, and it's precisely the functors that preserve the terminal object and send the distinguished pullbacks to pullbacks, and so functors into set. And so now I'm just turning that around, and I put op here because the C is a co-clan. So a model of a co-clan is a functor that sends 0 to 1 and sends these co-display push-outs to pullbacks. And so I want to view the models of this co-clan of finite direct categories as context structures. So and the idea that I have in mind is that if you have a certain well-behaved theory, then the context of the theory should be contravariantly over the shapes, because if I have a context of a certain shape and I have a discrete fibration, then I can rename the variables in the context, and so the variable renamings then give a context of the larger shape. And if you think about it a bit, then maybe it appears reasonable that we want exactly that we one shape, one context, one empty context, and also we want this push-out pullback condition that somehow means that we can build up larger contexts from smaller ones. And so this could give rise to a refined representation of generalized algebraic theories, or refined algebraic representation, where we could represent algebraic theories as certain monads in bimodules, and that's only for maybe people who have already seen similar ideas. So there's this paper by Fiore, Gambino, Hyland, and Winskell, where they explain that how algebraic theories, non-dependent, arise as certain monads in a Kleisli category of profunctors, where the Kleisli category is for the free finite product completion. And so my hope was that you could do something similar here, but I will not elaborate this in the following, and instead give another interpretation of models of this co-clan FDC of finite direct categories, which is very close, it turns out, to ideas from Chaitanya's thesis. And this is about locally finite direct categories. So a locally finite direct category is a small category, all whose slices are equivalent to finite direct categories. And so I write LFDC for the category of locally finite direct categories and discrete fibrations. And turns out that for every locally finite direct category, we can define a functor to finite direct categories, which just sends every object to the slice. And so we have to be, to readjust it a little bit because the slices are only equivalent to finite direct categories in general. And therefore, so this construction gives a fibration of groupoids over FDC. And so the models of the Coquelin FDC turns out are precisely those locally finite direct categories where this fibration of groupoids is actually a fibration of sets or of zero truncated groupoids. And initially I missed this point that they can be groupoids and not just discrete fibrations. Thanks to Simon Henry to point that out. So it turns out that Chaitanya considered also something that I think he also calls locally finite direct categories, but I want to call direct locally finite categories because his definition is a bit more restrictive. So a direct locally finite category is globally direct and has finite slices. So this is this finite fan-out condition that Josh mentioned. And so there are here two examples of things that are locally direct but not globally direct. So for example, if you take the index category of symmetric graphs, so that's, might know that graphs can be viewed as presheaves on the parallel pair category. But now if we put an automorphism, an involution on the over one object, then we get something like symmetric graphs. So graphs where we have some kind of, can turn edges around. So this is locally direct but not direct. So if you think about it, the slice over one is equivalent to this lambda, or this triangle. And so the terminal locally finite direct category is the category of finite direct categories with a terminal object. And this is also locally direct because the slices over a category are just the category itself. But it's globally the category has automorphisms. So I don't know how to distinguish this terminologically. If you think about this lambda category, it has an automorphism, but not as an arrow in the category, but as a category. I don't know how to say that, but I hope you get what I'm saying. And then here's a fun observation. So this category, and this should actually be the restricted category with additional discreteness condition. So this category of locally finite direct categories with this discreteness condition is actually a presheaf topos because it's precisely presheaves on this guy. And so I want to give an analogy. So if you look at topological spaces and local homeomorphisms, thanks. So topological spaces and local homeomorphisms almost form a topos, except that there's no terminal object. So here, that's very similar, but here you have a terminal object because you have by this finiteness constraint, you have the sizes under control. Okay, and concluding thoughts. So coming back to GATS, if you want to think about GATS with well-defined shapes of contexts, well, there's a problem because we have a definitional equality, and that may identify contexts of different shapes. So it can be that you have something depending on a variable twice, but then there's an equation where on one side the variable only appears once, and then the shape is not well defined of this equivalence class. And so the GATS where the contexts of a well-defined shape, well, they seem to be kind of linear. That's a linearity condition. And again, a final shout out to Chaitanya. I expect this to be related to some ideas on linear GATs of his. Thank you for your attention.
Okay. Thank you, Jonas. We have time for questions.
I was wondering where we want to, like, what's your envisioned place where you want to use this? Because my initial idea, for example, was that you would first consider the shape and then the context, but now it seems you want to compute the shape because you want to. So I just wonder, like, what's the goal?
Yeah, that's not entirely clear. So I'm interested in a refined notion of generalized algebraic theory, maybe. And at some point, I thought that you might get something equivalent to generalized algebraic theories, but not by this observation that I gave in the end. It's actually not equivalent because not all generalized algebraic theories can be represented this way. So on the one hand, it's supposed to be a restricted class of generalized algebraic theories. On the other hand, I mean, initially I also thought about implementations, because if you implement type theory, you don't store context as lists, but you store some explicit dependencies. And so I thought this is kind of a more realistic representation of what's going on, maybe, but I'm not an implementer.
So there also, actually, I was wondering if, because when you're actually type checking, you just bind variables and then whatever gets bound gets put in the context. And when you're type checking a lambda abstraction, for example, you would just say, well, the domain of your lambda, we're going to type check it in the entire context. So if you, like, from the viewpoint of a type checker, if you don't know what the user is going to do, you actually do end up with linear context, with a linearly ordered context. So I wonder if you've thought of what a type checker should do to actually carve out a more interesting tree structure.
I don't know a lot about implementing type checkers, and there's no binding here so far. So that's I don't have anything to say at the moment.
So I have a question. I'm a bit confused because there are two dimensions of context here. I mean, if you look at a GAT, then you have the horizontal and you have the vertical. I mean, line by line.
So yeah, you can view the entire GAT as some kind of. So, for example, if you take a GAT that has only sort declarations, then we get something that Josh called a dependency context, and that would be vertically. And that's why I'm said that my take on context is slightly different, because I'm looking at the horizontal.
The horizontal, right?
Yeah.
That's what I wanted to clarify. It's okay. Thank you.
I wanted to try and understand a bit better your remark that, like, if you take the push-outs in both sets, things do not really behave well. Because, like, at least from the implementer's point of view, it makes sense to say that context is some sort of DAG rather than a linear thing. But then if you think of DAG, you can only, dependency is an H prop, right? It's like you depend on this variable or you don't. And here you make it somehow proof relevancing, that you can depend multiple times or something like that. And I wondered, how does this manifest that you really need this kind of duplicate dependency somehow?
So I think I had an explicit example, where something would go wrong, but I don't remember the explicit example. Maybe I'll remember it later, then I'm going to tell you where in my picture what doesn't work with posits.
Okay, thank you.
Okay, let's continue the discussion in the break. We will resume at 11:40. Are there any announcements before that? Yeah.